Okay, so hello everyone and welcome. I'm Serafim Alvanidis and part of the UMM group from the beginning and hopefully in the next phase as well that Carmen will talk about. And it's a great pleasure today to introduce Martin Fleischmann. So I'll say a few words about Martin before he takes over and presents his fascinating work. Martin is a member of the Urban and Regional Laboratory at Charles University in Prague, where he leads a research team on urban structure. He's also a research fellow at the Geographic Data Science Lab at Liverpool University. He completed his PhD at the University of Strathclyde in Glasgow, where he focused on urban morphology and quantitative aspects of looking at cities, at characteristics of cities and how they evolve. He also holds degrees in urban design and urban architecture and urbanism. So his research interest lies in urban morphology, spatial data science. He focuses on quantitative analysis and methods, classification of urban forms, remote sensing, and bringing architectural aspects of cities together. When not doing research, which I also consider doing research, what follows, he is actually developing open source software and promotes open science. He is the author and the maintainer of a range of open scientific software tools, for example, MOMPI, which is the open source urban morphology toolkit for measuring urban morphology aspects in Python. He's also a developer of GeoPandas. There is Pandas in Python, which some of you may know about, but GeoPandas is focusing on the geographical aspects. And more recently, he has joined also the PySal development team. Now, all these things may not mean anything to you, but you can attend the Friday workshop where Martin will present the focused work around Python tools, and then it will all make perfect sense. Most of this information can be found on Martin's website. What is not there, though, is that in 2022, Martin and three co-authors from Strathclyde University were awarded the Breheny Prize for the most innovative paper published by the journal Environment and Planning B, Urban Analytics and City Science. Their article was entitled Methodological Foundations of a Numerical Taxonomy of Urban Form. It is available open access online to be downloaded and read. I think they explain most of what you need to know about urban morphology there. But what I wanted to highlight is that the article runs over 17 pages, which is quite long for an article in Environment and Planning B, after being asked to cut it down because they're quite prolific, which means that they put all this information, the rest of the information, in a supplementary material which runs over 30 pages. And in typical Martin Fleischmann fashion, once you finish reading the paper and the supplementary material, at the bottom there is a note. The reproducible Python code is available in the form of Jupyter notebooks, so you can play with it. And the work is accompanied by an open source Python package, which means that whatever Martin does basically is available online, open source, open access, open science to download and play with. It is a great pleasure today to have him here to present the work on the emergent structure of cities. Martin, you have 45 minutes and you agreed to take questions in the end for about 10 minutes. Is that okay?
Yes.
Okay, so I'm handing over to you. Thank you very much.
Thank you, Serafim, for a very kind introduction. I would like to start with an apology because I was hoping that I will be standing in the same room where you are right now, in front of you, in front of the screen. I will be presenting in person, but unfortunately there were some family matters that prevented that, and I'm not able to travel right now. But luckily, we have the means of the modern technology, so I can deliver the keynote and the workshop tomorrow online as was scheduled originally. The presentation I'm gonna talk about today is looking at urban morphology and looking at structure of cities. And while I'm currently based at Charles University, most of the work was actually done together with Danny Aribas-Bell at the University of Liverpool, where I was based before. So let me start with a brief introduction into urban morphology. because the field itself is kind of fairly enclosed, I would say. A lot of people are dealing with urban morphology, but the kind of formal entity that looks into urban morphology, which is the International Seminar of Urban Form, has their own ideas how urban morphology is defined and what are we actually dealing with and how. So let me just very briefly give you some introduction into the topic I will be talking about, so we all start from the same page. The very first definition, which is currently being used, is coming from Anvernes Moudon from 1997, from the paper which was introducing the International Seminar of Urban Form. And they very broadly say that urban morphology is the study of the city as a human habitat. That means a lot of things, and a lot of research actually falls under this umbrella. 20 years later, when Karl Kropp, when another of the prominent figures of urban morphology, wrote his handbook of urban morphology, he defined the field as the study of human settlements, their structure, and the process of their formation and transformation. So which is very much following what you were talking about in the introductions of the UrbanMetaMapping project. So I would believe that this is kind of very, very much on topic. But you can see that it slightly narrows down the breadth of what urban morphology is. But very often we are not dealing with these kind of complicated definitions, and we can simplify the whole explanation of what urban morphology is, that it's the study of urban form, of the built-up environment in cities, towns, villages, and other types of settlements. And historically, there were prominent ways of analyzing urban form. There are prominent methods and schools of thoughts. And urban morphology in its origins, which is kind of not entirely precise when the field started, but the main figures started publishing in the 1970s. And they established one school which is called typomorphological. That's a school coming from the Italian group of architects. And it looks into urban morphology from kind of a bottom-up approach. So they look into the individual buildings, into the plans of internal structure of individual buildings, of facades, and how they kind of interact with buildings nearby. And from this kind of internal understanding of individual buildings and their relations, they build up the understanding of the structure of a neighborhood, for example. At the same time, there was completely different school emerging, this time in the Great Britain. And the school is called historical geographical. And we can call it kind of a top-down approach because these people were geographers. And they were not looking at individual buildings and their plans, but they started from the plan of the whole city, and they were starting to break down the structure of a city using the information they had about the plan and about the evolution of the place into subsets, into zones of specific characteristics. In the meantime, since these all started in the 70s, there were a wide range of other types of analysis, notably, for example, space syntax, which is very prominent school based on the work of Bill Hillier and Julie Hansen from the UCL, which has started to bring computational aspects into urban morphology, but based primarily on street networks. There is a very prominent French school of urban morphology, and you will find a lot of other groups dealing with urban morphology in the last 50 years. But in the last, let's say, 10 to 5 years, we have seeing a new school of analytic approaches into the urban morphology, which is called urban morphometrics. And that's what I've been spending last, how many? 7, 8 years with myself. So today during the presentation, you will hear a lot about urban morphometrics. So what is it? It's kind of complicated name a bit. But it's essentially a study of urban form through the means of quantitative assessment of the constituent elements of urban form. So in practice, what we are doing is that we are taking the individual features we see in the city and we're measuring them. Conceptually, it's similar to the original historical geography approach, where we are looking at the whole plan of a city at the same time and trying to break it down a bit. But methodologically, it's completely different. It's embedded deep in spatial data science and geography, quantitative geography, and it's I would say, primarily data-driven. I've seen in some cases a bit of mixed methods linked to urban morphometrics, but what you will see in literature is that urban morphometrics essentially means throwing code at data, trying to understand cities, which is what I'm essentially doing. So we need to take something as complex as a city, as complex as urban form, the structure of a city, the physical environment, and turn it into something software can understand. So the first question we have to ask is, how can we actually conceptualize urban form for data science? There are different methods, different ways of doing so. You're probably aware that a lot of work is emerging around the use of satellite imagery. But I wouldn't necessarily call the type of research that is depending on satellite imagery primarily urban morphometrics. It's depending on the use case. It's slightly different approach. So I will omit the satellite part of representation of cities, and I will introduce fundamental elements of urban form as they are defined in generic urban morphology and then applied into urban morphometrics. There are 3 fundamental elements, first of which are buildings. If I need to work with buildings within data science frameworks, I need to have them represented as geometries. So this is a portion of Prague. It's very near from where I'm currently sitting right now. But this is the typical example of how buildings are represented within our use case. We do have every building drawn as a single polygon, usually a very simple polygon. It can be just 4 corners, and that's it. If we are lucky, we have some additional information attached to each polygon, like building height, building age, maybe use. But very often we just don't have anything. We just know at this location on Earth, there's a building, and it is joined with another building, and together they form blocks. But that's the whole information we are starting to work with. Second of the fundamental elements are streets. In data science, those are represented as lines. And those lines are usually trying to capture the center line of the street space. I will, in a few minutes, get a bit deeper into the issues with how streets are actually represented and what needs to happen before we can actually use them. But contrary to buildings, which were polygons, so we knew that this is an area covered by the building. With streets, we very rarely have this type of information, so we know this is where the network lies, Occasionally, we know what is the building, what is the street width on each segment. We know, for example, hierarchy of the street. If we are looking at some source that is able to distinguish between different hierarchies, we may know the pavement type, we may know different things, but this type of information is in most cases very inconsistent. So what we are trying to look into are solid geometries representing the center lines which join at junctions. And the last of the fundamental elements of urban form are plots. Plots are mostly represented as cadastre data, as cadastre layer, and those are representing the piece of land that is usually occupied by a building and its surrounding area, like a courtyard. And in this case, you can see that there are plots representing different street spaces, and that we can read to a degree similar structures we were able to read from the building layer, from the plot layer. But conceptually speaking, plots are what comes first and the buildings are what comes the second, as the plot is the driver of the building process, as the theory says. So given this type of representation of city, which is not a lot to work with, what can morphometrics tell about cities? Let me start with what we can actually get out of these individual elements on their own. So let's start with the question, what can we learn about a single building? If we zoom in, let's say that we are looking at this corner building in here, it's a very simple polygon. We can see its rough shape. We don't see a lot of architectural detail on it. We don't have any information about building height, age, use, or anything like that. We just know that somewhere here is a building which looks roughly like this. And if we don't know anything about its surrounding, we can't really answer a lot of questions about these buildings. But we can, for example, ask about sizes, about perimeters, about areas. So this is, for example, probably the most simple morphometric description of urban form, which is the building area. When I will be talking about these variables we are measuring, I will be using the term morphometric character, which comes from the original morphometrics, which wasn't at all urban morphometrics, because the whole theory and methodological approaches we are using in urban morphometrics are coming from morphometrics, which was used to derive taxonomies of birds and plants in biology before biologists were able to sequence DNA. So when I was doing my research, the paper Seraphim was talking about before, I was actually reading a lot about different types of birds, different types of fish, and how they measure those and how to combine those together before I was translating the whole idea into urban morphology. That's where the term morphometric character comes from, but the character is essentially a piece of information about, in our case, environment. And building area is one of the simplest morphometric characters. We can also ask about different shapes of building polygons. And then we have a wide range of characters to choose from. We can look at shape complexity using something called equivalent rectangular index, and I will not go into detail into formulas how that's computed, but you can see from the map probably on your own that when the building has a more complicated shape, it tends to be ranked higher than those with the simplest shapes. And that's the whole point of this index. But we can also look into similarity of buildings to rectangles, similarity to circles, and quite a wide range of other shape indices, as the shape indices very often come from other fields of study, typically looking at gerrymandering in the election districts in the US, where they are doing very fun stuff, but we can then reuse it in our fields. But we can also look into spatial distribution of the buildings if you're looking at individual buildings on their own. If we're looking, for example, at building orientation, the way how we measure building orientation is slightly different from typical orientation stuff, is that we are trying to determine the deviation of the orientation of a building from cardinal directions. So the minimum value is 0 and the maximum is 45. But then we can understand whether the building is facing directly north and south, or whether it's rotated by 45 degrees. And you can see it on the map in here that it indeed is able to distinguish different patterns within the city already. So that's building. But what can we learn about street? I said that those are lines, and there are some issues with those. So the first thing we will learn while trying to work with the street networks is that whatever comes as a street may not necessarily be a street as we would like to talk about. This issue comes from the different needs of different groups of researchers. Very often when you are downloading a street network from sources like OpenStreetMap or from any governmental data portals, you will figure out that what you get is a transportation network. So whenever there is a roundabout, you will see a roundabout. Whenever there is a dual carriageway, like we can see on this part in here, you will get the dual carriageway. And in some places, in the US, for example, or in China, I've seen you have a lot of dual carriageways. And this type of representation is great for transportation analysis, but it's terrible for morphological analysis. Because what I need is that a single street space is represented by a single line. And therefore, there needs to be some level of pre-processing, which is unfortunately non-trivial to eliminate these type of transportation artifacts. And we have currently an alpha version after I think something like 4 years under in development of an algorithm that is able to do this for us. It's not perfect, but what you can see here is the input on the left side and the output of the algorithm on the right side. So this specific street is now represented as a single line, and this specific roundabout is eliminated from the network. The reason why I need to get rid of these is that, for example, when I'm joining buildings to streets, I need to ensure that buildings on the left and right side of the street are actually joined to the same line representing the street, which is not what would happen in here. And therefore, the information I would measure would be completely wrong. So that's the first thing you can learn about streets, that they're usually not streets, and we kind of need to do something about it. But once we have done something about it, if we are really lucky and you get a network which is not struggling with these issues, you can look, for example, at spatial distribution. As I was mentioning, we can join buildings to streets, and we can look at the street profile width. So how wide the street is when coming from building on one side to building on the other side. Or the openness, how large proportion of the length of the street actually looks into the open space where there are no buildings in there. You can see that on the right side in here. If you recall the building layer, there were very little buildings in here. So these are essential open spaces. We can also look at shapes, but slightly different types of shape analysis than for buildings. So we can look at the linearity of street geometry, you can see that this specific map highlights only few of lines which are not straight lines in here. But when we are doing this on the large scale, linearity, for example, is very good at picking up the dendritic patterns in US suburbs. But we know that streets are forming a network, so we don't have to look at individual streets as individual lines, but we can look at the way how the network is organized, which means that we can measure the connectivity of the whole thing. And when I visualize the result of one type of connectivity character, which is local closeness, you will see that the values are now not joined to individual lines, but they are joined to the junctions, to points where those lines intersect. And that's because a lot of connectivity type of analysis is reusing graph theory. It's reusing algorithms that have been developed for different purposes. And as a result, we are retrieving the information linked to individual so-called nodes of the network, which are representing junctions in our case. Another example would be a square clustering, which is able to identify the grid and rigid grid parts of the network compared to a bit more broken grids or no grids at all. Now, what can we learn about plot, which is the third of the fundamental elements? Again, you can learn that there are a lot of issues. Very often it's not available as open data. Occasionally it is. When it is, it very often does not represent morphology. This issue varies between countries a lot. But for example, in France or in the UK, if you are able to get plots, which in some cases you are, you will learn that the morphological meaning of a plot as a piece of land with certain boundary within which a certain type of development happens is not coinciding with the representation in the cadastre, especially in the UK, where a lot of historical centers, for example, were historically owned by certain nobility. You see very large plots covering whole blocks, for example. In France, you will see that in the single morphological plot is actually represented by 3 or 4 cadastral plots. That's actually the same issue in Czech Republic. That in the end you will learn that yes, plots are nice, but we can't really use them properly. And even if we have information on plots, which is nice and representing morphology, we will learn that the way how plots are representing morphology differs between different periods of development. So these are 2 places from Glasgow. And on the left side, you can see a neighborhood that has been built, I believe, in late 18th century, where if I remove the buildings, which are the dark gray color, I can still read the structure of a place by looking at the structure of plots, as the plots are the formative element in here. But on the right side, you see modernist development, where plots are essentially randomly allocated underneath buildings and slightly around, and they tell us very little about the structure. They do not hold the formative meaning any longer. So what we do with this, we forget about plots and we develop our own representation of space. We use something we call polygonal tessellation, and I will show pictures soon, as an analytical unit, which partially takes the role of a plot because it shares a subset of information about spatial configuration with a plot. And we've originally started with an approach called morphological tessellation, which would look like this on the subset of Prague we are looking at. And that essentially takes buildings and nothing else, and allocates space which is the nearest to each building. Like what Voronoi tessellation would do around points, morphological tessellation extends that and does the same around polygons. But that means that in some occasions, like where we have large parks, we have very large plots which are no longer representing the space as it should. Therefore, we have expanded the definition of morphological tessellation into something called enclosed tessellation. And while there's a very little difference, what enclosed tessellation does is that it first identifies something we call enclosures, which are areas fully enclosed by streets and other types of barriers. So we'll see that where that large park is right here, or large square is right here, they have their own definition of enclosed tessellation cell. And Voronoi-based tessellation around building polygons actually happens only within individual enclosures. So this is much closer to how plots would look like, and it very much resembles the structure of plots, even though the streets are always part of building tessellation cells and not their own. So what can we learn about cell if we don't have a plot? Again, we can look at sizes and shapes, longest axis length, which gives us the indication about the size of a cell, circular compactness, as you can see in here, that measures how similar the shape is to a circle. Importantly, we can derive contiguity from these networks, and you can see in black lines here a contiguity network representing that this polygon is a neighbor of that polygon, and that is a neighbor of that polygon. And because the tessellation cells are derived from buildings, we can link this to buildings, and we can identify which buildings are neighboring which, not only because they are touching their walls, but also because they are across the street. And with this type of information, we can start talking about not a single building, but buildings as a structure. So we can look at spatial distribution derived from this, and we can measure the shared walls ratio, the proportion of external walls shared by other buildings. You can see from 1 to something zeros, which are very invisible here, probably completely invisible for you. Building adjacency, how much the buildings tend to be joined together with other buildings. Again, you can see on the right side these single-family villas, which tend to stand out on this metric, or mean interbuilding distance. You can see that across the large open spaces or across the parks, the distance to the nearest building tends to grow significantly. So what happens if we measure a wide range of these things and combine them together? What can we do with this type of information? Why are we actually doing all of this? What's the point? Well, the first type of analysis we can do is the identification of a type of urban form. I got a couple of examples in here. This is Barcelona. We have taken buildings and streets from Barcelona. We have generated around 60 different morphometric characters. We did some data science magic on top of those, and we identified these 16 types of development in Barcelona. On the left side, you can see them projected on the tessellation cells, and on the right side, you can see them projected on buildings. And you can see for yourself that this type of algorithm very nicely picks up the famous example area, picks up the historical quarter, picks up the historical villages around different parts of Barcelona, and infill areas where the example was joined with existing urban structure, and the way how Barcelona is then try to kind of grow into the mountains surrounding it. We did the same analysis for Medellin in South America. Again, if we project this, you can start seeing that while tessellation cells are covering large area around here, there's actually very little buildings. In some cases, no buildings at all. We are able to read the structure of a city using this type of analysis. The same works in very wide range of contexts. So we try the same type of analysis in Singapore. We tried to do it in Dar es Salaam, in Tanzania. And I'm not going to show this on buildings because those are very, very tiny in here. And we also tried to do this in the US, but surprisingly enough, the US had probably the worst data we have worked with compared to anything around the world. Even Tanzania was much better represented than US building footprints. We can also use this type of information to predict urban phenomena, like the impacts of planned development. So if we do have a classification, like this one in the Tyne and Wear in the North England, and we also know the information about the house prices in areas and air pollution in areas. We can train predictive models based on morphometric information that can give us indication about a change of the, let's say, air pollution or house price, given certain development scenario, which can be represented as morphological change. So in here we do have an application that is able to test the impact of, in this case, what's on the map, densification of brownfields and the impact on air pollution. And I want to finish with the case of Great Britain, where we took all of this together and we tried to understand the structure of form and function across the whole island. Because we're looking at main Great Britain islands, so England, Wales, and Scotland. So we are looking at the data-driven overview of the British landscapes. We started with development of classification, like you just seen across different cities from the world. And we did it for the whole Great Britain. So we have 16 types of spatial signatures, 16 types of urban form, which are derived from, on one hand, a wide range of morphometric characters, but also influenced by information about function of each location, of each building in principle. So we are linking the data from the workplace areas to understanding the amount of workplaces. We are doing accessibility analysis. We were linking some information on the greenery levels in the area. And all that was kind of mixed together to identify distinct types of development across the whole country, which resulted in, as I said, 16 types of development. And you can see a city of London in here. You can see Liverpool and Manchester, or the Scottish Central Belt in here. And if we unpack this a bit, we will learn that those 16 types of signatures can be split into 3 larger groups. First are rural signatures. Those are those which do not necessarily represent urban context. We have wild countryside, we have agriculture, and we have something called urban buffer. And these 3 together cover 94% of land, but only 50% of tessellation cells, of which are the main unit of analysis. The second group of signatures are so-called peripheral signatures. Those are those which are representing development which is not entirely urban, but it's not rural. It's kind of the peripheral type of urban development. And we have four, mostly representing different types of suburbias and sprawl, but also warehouse areas. And those together cover 5% of land, but 40% of enclosed isolation cells, which means that while they are relatively small in terms of extent, they are dominant in terms of the within urbanized contexts, within the number of cells or number of buildings belonging to these. And nearly half of that is falling under the category called open sprawl. And the last of the groups is called urban signatures. So those are those signatures which are essentially covered, representing what is urban in the Great Britain. And we have a large number of those, but as you can see, some which are called urbanity, which are the most urban, which are the centers of large cities, are very, very, very rare. So all urban signatures are covering 1% of the area of the Great Britain. They take up 10% of cells. And out of these, we are still talking about mostly residential neighborhoods, rather than something like city centers, which are indeed extremely rare in the context of the whole country. What we tried next is to look at the spatial distribution of signatures, and we were able to derive a hierarchy of those based on the spatial distribution and based on the collocation. So I have a figure here, which is, I admit, a bit complicated, and it's also a fair bit technical. So let me just explain that on the left top corner, you see the whole map of the Great Britain. Here, for every signature, you see the distribution across both latitude and longitude. And this large grid in here represent how a large proportion of neighbors of each signatures is with any other signature. So we'll see that, for example, hyper-concentrated urbanity type is sharing its boundary only with concentrated urbanity. That concentrated urbanity is sharing its boundary with hyper-concentrated, but also with the metropolitan urbanity. And if we use the banding algorithm in here, we are able to organize the types of spatial signatures into data-driven hierarchy from wild countryside to hyper-concentrated urbanity. And that will be useful later on. But before we get to where it's actually useful, we looked into settlement delineation. So we start with buildings with some barriers. And as I showed here, we are able to split those into different subgroups. And this one is showing the rural signature types. But you can see that there's an interesting negative of this. And if we combine the signature types of urban and peripheral, which is what's missing on this one, we actually can use this to delineate urban areas, which is what we have done. In the UK, we have nearly 1,000 settlements. And if we compare those to functional urban areas from the global human settlement layer, we can see that signature-based settlement delineation, which is in blue on this figure, is much smaller, and it's much more detailed compared to functional urban areas, which are based on population grids. And This led us to definition of settlements, and because we also had a hierarchy of signature types, we started looking into the hierarchy of individual settlements across the whole country. And that had essentially a very simple approach. So we looked at our signature types, excluding those rural ones, and we looked at how much of a land of each settlement, of each city or town, is covered by the most urban of the signature types, which is the hyperconcentrated urbanity. And then we looked at how much is covered by concentrated, how much covered by metropolitan, by regional, by local, and so on and so on. And you quickly learn that hyperconcentrated urbanity and concentrated urbanity are present only in London, instead of Westminster. It's nowhere else across the whole country. Therefore, this one is probably the top in the hierarchy, as you would kind of expect from London. Then you will learn that there's a small subset of cities where we see metropolitan urbanity present, which is the third on the hierarchy. Those are places like Birmingham, Edinburgh, Glasgow, Bristol, Liverpool, together with Manchester and Salford, which is in our definition a single settlement. And then we move on to places like Plymouth, Sunderland, Aberdeen, where the top signature type is regional urbanity. And then we can go further down and down and down. And this single diagram is showing every single of the settlements in the US, in the UK or in Great Britain, and where they sit on the hierarchy of settlements. And this can be translated into something a bit more visual. So we have derived this type of visualization we call signature dishes, where we take the area covered by each of the few of the top signature types, and we show it both geographically and diagrammatically what the importance and extent of these centers are. So we see that London is by far the largest, most important center. It's the only one on the first type of hierarchy. And then we get further down to Glasgow, Edinburgh, Liverpool, and so on. And you'll also start seeing some differences, for example, between Scottish cities, which tend to be more densely built, which means that their centers have the least amount of kind of the yellow dense residential neighborhoods type compared to, for example, places further south in England. And we can start looking at hierarchy of settlements which emerged from the initial analysis of urban morphology, which emerged from individual buildings and individual streets. And we went all the way from measuring areas and linearities of street segments into something that can be used potentially to guide policy and to subdivide a complex settlement structure into something more and more manageable. And as again Seraphim said, everything we're doing is open and reproducible. So this whole project called Urban Grammar AI has a website. The website contains all the code we've used to do every single piece of analysis. It contains multiple repositories. It contains the archive of all the public talks, in most cases with recordings, because the project happened mostly during the COVID times. We do have websites which are trying to translate the complicated academic jargon into user-friendly explanations of what spatial signatures are, what the classification is about, how it's built, and what you can do about it. We do have released everything we have generated as open data products, and we have contributed a lot to both existing software like MonPy, which is specifically designed for morphological analysis, but also to other types of software. And we have also released one package which supports the underlying clustering analysis as its own package. So everything we have done is available. If you would like to do this type of analysis on your own city, on your own country, you're free to do so. We do have reproducible environments, and everything is up there. It's up there in the open, and all the publications are currently open access. Which leads me to the final part of the presentation, which are the takeaways. So how can we summarize all those 45 minutes I've been speaking? Urban morphometrics, which is the subfield of urban morphology, sees urban form as data. And we can use the data science approaches to analyze them. This allows us to scale the analysis of urban morphology to entire countries and possibly beyond. And we are currently working on a project which does morphological analysis across the whole Central Europe, including Saarbrücken. But unfortunately, we are nearly there. But I wanted to show it, but it's not ready yet. So hopefully next time I will show how Saarbrücken looks through the lens of urban morphometry. The information collected on individual elements of urban form can explain the structure of neighborhoods, which is what we would expect, not cities, but also the hierarchy of settlements of entire regions. And when we go across different boundaries of different regions, for example, if we cross from Germany to Czechia, Slovakia, Poland, we are actually able to start reading the historical boundaries that used to be there in the way how our cities are structured. And because all of this is technical data science, it all can be open, it all can be reproducible, and all can be reused. And that's all from me. I would love to have a discussion right now, and I would love to have discussion during the next 2 days, but unfortunately, I'm not there. So if you would like to follow up, please use any of the means you are able to find, email, social media, whatever you will find, or find Lisa Winkler, who should be speaking just after the coffee break, who is working with me, and just connect with her, and she will make connection through to me. So that's me. I believe we have about 7 minutes for discussion. So thank you very much. And I'm eager to hear any questions and comments, and enjoy the conference. Thank you.
Thank you, Martin. Questions? We have a microphone, hopefully.
Hello?
Yes, does it work? Martin, can you hear this?
I think so.
Okay. Okay, any questions then?
Yeah, hi. I'm Jonas Lied from Geses Leibniz Institute for the Social Sciences. And I have a question on your project on urban grammar AI. And at the beginning of your talk, you talked a lot about all of these urban morphometrics indicators and how to basically apply them using traditional spatial analysis. But at the end, when you introduce the Urban Grammar AI project, basically it says AI in the title. So my question would be, is the project based on traditional spatial analysis, or is it based on more advanced AI techniques?
I have talked about only one part of that project, which is built on traditional spatial analysis, spatial data science. The second part of the Urban Grammar AI project, which is where the AI comes in, was looking at application of satellite imagery and trying to understand whether we can detect spatial signatures from satellite imagery and whether we can use the time series of satellite imagery to unfold the evolution of cities using the spatial signatures framework in time. So that's where the AI sits within this project. I didn't want to talk about it because those are two kind of distinct topics, but that's the AI part. The stuff I've been talking about, everything regarding the classification, everything regarding the hierarchy of settlements, that has nothing to do with what I would necessarily call AI. So there are no neural networks involved in there.
Thank you. More questions? Coming.
Thanks. Olga Kellert from University of Göttingen and A Coruña, Spain. My question is, you started in the beginning saying that you don't have the information about the function and use of the buildings, whatever, right? But then you ended up with showing nice outcome of your analysis using functionality, right? So like residential, I mean, this is functional. So, and my question is, okay, what kind of information do you actually get from the maps? So it's not just the shape. So you started, we just have mathematical geometric, basically, information, but then you do have some kind of functionality. So I guess, yeah, that's my question. What kind of information do you actually use? And would your analysis be even better if you get more information that you could link more and more basically geometric and functional use of the buildings or streets or whatever?
That's a great question. And the answer is that it depends. So in certain occasions, we have purely only the geometrical information about buildings and about streets. And the fact that the final classification can be interpreted as this is industrial zone, this is residential zone, has nothing to do with the fact that this type of functional information was embedded in the data, what was actually explicitly embedded. It's just implicitly represented by morphology. But the truth is that in the case of spatial signatures, we try to include additional information than form only. It was occasionally linked to certain types of land use. Spatial signatures is a concept that is relatively open in terms of the definition of what comes in, because what you can do in Barcelona is very different from what you can do in Houston, Singapore, or Medellin. So the amount of information that's embedded in that changes. Within other projects, we are dealing with building footprints only and street networks only. So we do not have any of this information. And we learned that urban morphology has the power to encode a lot about the environment. And for example, if we compare the classification of Barcelona using purely the geometry, but the one which is derived also from functional information, there's very little difference. So our conclusion, which kind of affected how our current projects are being developed, is that we essentially don't need much. more than geometry. We don't even need building height because, as some colleagues have proved, flat 2D morphology is able to predict building height with very high accuracy. We don't need building age because, again, morphometrics can predict building age within the neighborhoods. And yeah, so we are pivoting to using solely geometrical information again.
Thank you. I will take, okay, there's 2 questions, and are there any more, just to plan the timing? Okay. Okay, we'll start here.
Hello, my name is Shanyal from Frankfurt Zoological Society. I have a follow-up question from my colleagues. So you said that we can use this code of yours to carry out similar analysis. Do you think that if we induce like satellite images, so with that we can also induce like drone images and carry out analysis? Will that help to get better analysis in terms of city or not?
Well, first of all, you will have you have to figure out how to link the 2 types of information. There are ways of extracting the data from satellite into a meaningful set of dimensions, but it's non-trivial task. But assuming you are able to link this type of information into the spatial unit that can also be used for the vector type of analysis I've been showing, I believe it will improve. What we've seen is that this type of analysis is unable to capture the amount of green and blue spaces. So it doesn't see a difference between neighborhoods which are full of trees and greenery and those which have no trees at all. Because this type of information is missing unless you explicitly include this. And that's where imagery helps a lot. So yes, I can imagine that additional type of information, be it satellite, aerial, drone imagery, or anything you may have, will help. But eventually, you will get to the point where the difference in the result with and without the additional type of information is so small that it's not worth the effort. So typically, I would try to do the analysis with some focus in mind, and I would look at whether the result is actually reflecting what I'm trying to capture in a city. And if it does not reflect, I would try to include additional information which I know or I have a hypothesis about that is it's going to help. But I wouldn't necessarily try to throw as much data as we can on the algorithm and hope for the best, because too much data is also an issue.
We're eating into the coffee time, but I'll take one final question. Short, please, and short answer.
Okay, thanks, Martin. I'm Michael from Newcastle upon Tyne. So I was going to ask you a very simple question about any dynamic element to the morphological approach, because you mentioned cells, and it got me thinking about cellular automata. So is there a dynamic element to different eight strata, or is it a static model?
It's a static model. The issue with dynamic models is that you would need to have the data representing morphology in the same quality and resolution and detail for different times, different points in time, which is just simply not available these days. The growth of urban morphometrics is very much tied to the growth of availability of open data, and this type of information in the resolution we need has been around for 5 years, occasionally more, but very rarely. Therefore, we just don't have that information, what happened 10, 15, 20 years ago. That's why the satellite imagery should help. And that's what could potentially bring a time dimension into this. But at the moment, there is no dynamic element to this. It's mostly static.
Thank you all for your excellent questions. Thank you, Martin, both for answering and for the presentation. If you would like to know more about how to do this, Friday, 2:30 until 4 o'clock, and I'm sure Martin will be able to answer more questions.
Yes.
Okay, so thank you again. And yes, we really appreciate the fact that you made time for us and presented the keynote. Thank you.
Thank you.